In this presentation, I will demonstrate how the choice of polynomial basis affects numerical stability in regression. I will compare the standard Vandermonde basis with the Legendre polynomial basis using a real-world medical dataset. Why study polynomial basis? Polynomial regression can approximate nonlinear functions, fit complex patterns, and increase flexibility with higher degree. But high-degree polynomials often become unstable. Polynomial regression, given data points xi, yi, we model as y is equal to a naught plus a1 x plus a2 x square up to ad xt. In matrix form, y is equal to va, where v is the design matrix and a is the coefficient vector. Bond basis. Standard polynomial basis in matrix form can be written like this. As degree increases, columns become highly correlated, matrix becomes ill-conditioned, and small noise leads to large coefficient changes. In Legendre polynomial basis, Legendre polynomials P and X are orthogonal on -1 to 1 range. They reduce multicollinearity and improve numerical conditioning. Dataset used. I use diabetes dataset from Skyscraper. This dataset contains medical measurements from 442 patients. The target variable is disease progression after 1 year. For simplicity, I selected one feature, BMI, to create a 1D regression problem. The goal is to fit polynomial regression and compare numerical behavior between two different bases. Coming to the code walkthrough, in the first block, I import necessary libraries, NumPy for numerical computation, Matplotlib for visualization, scikit-learn for dataset loading and splitting, and NumPy's Legendre module for orthogonal polynomials. In the block 2, I load the diabetes dataset. I select the BMI feature, which is column index 2. The target variable is disease progression. This creates a simple non-linear regression problem. Coming to block 3, I split the dataset into 70% training and 30% testing data. This allows us to evaluate model performance on unseen data. Before fitting, before fitting Legendre polynomials, I scale the BMI values to the interval -1 to 1. This is important because Legendre polynomials are orthogonal on the interval -1 to 1. Proper scaling ensures good numerical properties. Here I define two functions. The first function constructs the Vandermonde matrix using powers of x. The second function constructs the Legendre polynomial matrix using orthogonal basis functions. Both functions solve the least square problem and return predictions. Condition number of the design. The condition number measures numerical stability. I set the polynomial degree to 10. Then I train both models and compute the test mean squared error. I also compute the condition number of each design matrix. Typically, the Vandermonde matrix has a much larger condition than the Legendre matrix. The plot shows the model predictions. The gray points are the training data, black points are the test data. The Vandermonde fit may show slight oscillations, while the legendary fit appears smoother. This suggests improved numerical stability. Condition number versus degree. In this block, I compute the condition number for polynomial degrees from 1 to 19. The graph is plotted on a logarithmic scale. We observe that the Vandermonde condition number increases rapidly with degree, while the legendary condition number grows much more slowly. This confirms that orthogonal bases improve conditioning. Coming to the conclusion, this experiment shows that polynomial regression is sensitive to the choice of basis. The Vandermonde basis becomes ill-conditioned as degree increases, leading to numerical instability. Legendre polynomials, due to orthogonality, provide better conditioning and more stable conditions. Even though both models represent the same polynomial space, their computational behavior is very different. This highlights the importance of numerical linear algebra in real-world machine learning problems. Thank you.